Useful factoid for later. Very often an object will rotate about its center of mass. We'll talk about that because it ends up being the rotational inertia is least about the center of mass, and therefore it is easiest to rotate there. Most especially if an object is not constrained to rotate about some other point, by say a pin or a pivot or a hinge, then all forces exert torques about the center of mass. And as an aside, remember that the definition of the center of mass is that the total mass times the center of mass position is each individual mass times its position summed. And you would do that in x and y and z separately. If torque is the analogy of force, we would expect a net torque to produce an angular acceleration, just as a net force produces a linear acceleration. And this is in fact true. It's expressed in the rotational analog to Newton's second law. The sum of all the torques is I alpha. You might also see that written sometimes as, of course, tau net. Exactly along the lines of F equals ma. Two pulleys with different radii labeled A and B are attached to one another so that they rotate together. Each pulley has a string wrapped around it with a weight hanging from it. The pulleys are free to rotate around a horizontal axis through the center. The radius of the larger pulley is twice the radius of the smaller one, i.e. B is 2a. And the heavier mass is 1.5 times the lighter mass. The student describing this arrangement states, the larger mass is going to create a counterclockwise torque, and the smaller mass will create a clockwise torque. The torque for each will be the weight times the radius, and since the radius for the larger pulley is double the radius of the smaller, but the weight of the heavier mass is less than double the weight of the smaller one, the larger pulley is going to win. The net torque will be clockwise, and so the angular acceleration will be clockwise. So let's evaluate each of these things. Is it true that the larger mass creates a counterclockwise torque and the smaller mass creates a clockwise torque? Well, for each of these things, the line of action is clearly vertical because the force on the pulley is each of the weights. Well, the tensions produced by the weights, we need to be careful about that. But at least when we first release it. And let's see. And then, of course, the moment arms are just going to be the distances to those lines, which is the point of applications. So let's see. So this guy does produce a counterclockwise as we pull down this way. And this one does produce a clockwise. So that statement was right, at least. All right. Is it true that the torque for each is the weight times the radius? Yep. Whoops. That's certainly true. Now, so we have that the smaller mass produces a torque which is mg times b, or mg times 2a, or 2mga. And the heavier mass produces 1.5 m times g times a. And it's definitely true that that 2 is more than 1.5. So the student is, in fact, correct. That's sort of unexpected in these problems, but it happens from time to time. We define a state of static equilibrium to be under which the system undergoes no accelerations. That is, the forces are 0 and the torques are 0. One conventional facet of static equilibrium is choice of rotational axis is entirely arbitrary. You can pick wherever you want. If there is an actual rotation going on, you should make the axis of rotation the point at which that rotation is occurring. Otherwise, you get really messy reference frame effects, and it's really kind of annoying. So we're going to do a classic thing called the flagpole problem. Consider a flagpole of mass m and length L connected to a building by a pivot which is free to rotate. Keep the pole horizontal. A cable is run from the far end back to the building to make an angle theta with the horizontal. And I want to find what's the tension in the cable and what upward force does the pivot exert on the pole. And the pivot must exert some upward force on the pole, or at least we think it may, because otherwise the weight might bring it down. So we draw our free body diagram as always, and we evaluate the torques about the pivot point. We don't have to because there's no rotation going on, but I choose to because I get a whole bunch of zeros that come out later. So from our free body diagram, the forces in the x are the pivot pushing to the right and the tension pulling to the left. And the forces in the y are the pivot or the weight pulling down and the tension pulling up, and at least potentially a force from the pivot pushing up as well. We don't know yet, but it's at least in principle could be there because it's in contact with the wall. And then the sum of the torques, the net torque, would be FPX times its moment arm, but it's pointing through the pivot, so the moment arm is 0. And FPY times its moment arm, but it's pointing through the pivot, so its moment arm is 0. And FTX times its moment arm, and even though it's a full length away, it's pointing through the axis, so its moment arm is 0. So we get rid of 3 things by putting the pivot at the actual hinge, and so that makes life easy for us. We're left with the tension, whose line of action is vertical, and the weight, whose line of action is vertical. For the tension, the moment arm is just the length of the rod of the flagpole, and for gravity, the moment arm is just half the length, and so we have the L and L over 2. Why do we have the minus? Well, the tension tends to pull the thing clockwise, but gravity tends to pull it counterclockwise. And the fact that we're in equilibrium, we have F net equals ma, but a is 0, and tau net equals I alpha, but alpha is 0. So we can put all these things together and do a standard amount of silly algebra tricks. We can take this one, doesn't help us very much at all, but here we get that, here we can say the tension times L, the y component tension times L minus the weight times L over 2 is 0. So we get that TYL equals FGL over 2. So TY is a half mg. And so sine of this, Ft sine theta is half mg. So the tension must be mg over 2 sine theta. And from this one, we get that the force pushing upward has to be equal to the weight minus Fty. Hey, we found Fty is a half mg. So the pivot must also be putting up at half the weight, which is not surprising, right? We need to support half the weight at either end or it will spin. All right, the balance principle. An object or collection of objects is in balance when its center of mass is directly above or directly below the point of support. In such case, the force of gravity passes through the pivot point and has a moment arm of 0, so gravity will exert no torque and the object will remain balanced. This is also how things fall over. If you shift them so that their center of mass falls off of the off that vertical line from the gravity, then they'll tumble. This is illustrated in one of these videos from the textbook. So here we go.
Well, it seems that I've done something wrong, because now I'm up here getting ready to walk the plank. Fortunately, the plank has 90 pounds of weight at the far end, but it's also over the edge by 1 meter. Now I weigh 210 pounds, so if I were to walk out to the edge of the plank, would I be able to stay on the table, or would I fall onto the floor? Well, if you calculate the torques, 1 meter is too far. The plank is roughly 2 meters, and so 210 pounds at one end does not equal the 90 pounds at the other end. So the question is, with a 2 meter long plank, 210 pounds at one end, 90 pounds at the other, how far out can the plank be such that I can walk to the end and not fall onto the floor? 0.8 meters, 0.6 meters, or 0.4 meters.
All right, pause the video and take a second to actually compute that. Really give it a try. Here we go.
The answer is 0.6 meters. So here we roughly have 0.6 meters sticking out over the edge. And if I walk very carefully, making sure not to jump up and down, I am quite safe. So the 210 pounds times the 0.6 meters equals the 90 pounds times the 1.4 meters.
All right. Let's walk through and actually try and show the 0.6 that he gets. Here's our setup. We've drawn out the, here's the plank. Oops, here is the plank of a total length L. I'm going to do this in general. He did it for specific values. We're going to support a weight at a distance x1 and the person at a distance x2. And of course, the plank itself has mass, and that's the important bit. So its weight is pulling down on it at the center of it. And it's important that this is approximately right, at least, that this should be the center of the stick of the plank. So we see that the counterclockwise, the stuff that would tend to move us this way, is coming from this force, and their torques are each their distances times their magnitude. And the clockwise torque is coming only from the person themselves, and their torque is their distance times their force, at least at the moment. If it's going to be balanced, the net torque has to be 0, so these torques have to equal each other. But geometrically, we can see that x1 plus x2 is the total length, and that x sub g plus x2 is half the length, because the center of mass of the plank is at the center. Put those back in down here, and we find that we have x2, f2 being one thing, and L minus x2 times f1 plus a half L minus x2 times the weight is the other. We could solve these algebraically. I'm lazy and didn't want to do it that way, so I plotted the two torques and saw for what value of x2 do they balance. So the clockwise torque as a function of x2 does this. These would be unbalanced, but we can still compute it. Likewise, the anti-clockwise torque does this, and they meet at about 0.6129 with a torque of 61 something, which we don't really care about. So we find that they balance at 0.6129. You might wonder, why did he say 0.6 when it's really 0.61? And the answer is almost certainly because he used the British units with the 90 and the 220 and so on, and I used the statements that were in the problem, which were in metric, so it was something like 40 kilograms and so on, and 2 meters rather than feet and so on. The balance principle tells us that when an object is suspended from some point other than its center of mass, the center of mass will lie on the vertical line containing the pivot, assuming it's been allowed to come to rest. Right? If it's going back and forth, this is obviously not true. But if it's just resting there, then the center of mass will lie in the vertical line containing the pivot. So we can see this. This is some artwork my wife brought back when she was from overseas. It's supposed to be a vertical thing, but at some point during our moves, this hook came off and broke, and so it hangs this way, which disturbs her a little bit, but as a physicist I'm very excited by, because I can look at this as a balance problem. So considering the lower thing here, the center of mass of it, since this is basically symmetric, would be at the center of the rectangle they make. So something like that. And the pivot that they're hanging from is here, and we can see that that pivot does actually pass pretty close. That line containing the pivot does pass at least very reasonably close to the center of the hanging bit. We can use the balance principle to find the center of mass of an awkward body. Suspend the object from any point, allow it to come to rest and hang, draw a vertical line through that pivot point, suspend the object from some other pivot point and allow it to come to rest, draw a new vertical line through the new pivot point. Where the two meet is the center of mass. You should really do a third point, because the new line will go through your intersection as well, to ensure that you didn't randomly pick the center of mass, where you'll get some randomness out there. All right, so you want to make sure that one of your points wasn't the center of mass. All right, these piggy banks are identical but hold differing amounts of the same coin, and we want to rank the banks according to how much money each holds, which means essentially how many coins are them, which essentially means by their mass. To keep it balanced, the heavier object has to be near the pivot point than the lighter object. So if we consider that B and C together and forget A for the moment, for this bar to be balanced, with C being closer in, it must be more than B. And then they're going to exert a combined torque here, a combined force on this string, so I'm going to replace them with a box that has the same mass. And now we can see that A is closer to the pivot point than that frictional box is, so A must be more massive than the box. But if A is more massive than the box, then it's more massive than anything in the box. So A is more than C, which is more than B.